So I want to just talk briefly through this first example, because we've talked about how rectangles work, but we haven't talked about this yet. So you don't need to write anything on this first page, really. Is if you did a midpoint, this is an example of a midpoint Reimann sum, okay? Now again, what we did on this is we divided it up, but I want you to notice on this that if you went through and worked this out, all of your rectangles are below the x-axis, okay? And that's what we're going to kind of talk about a little bit, is what happens in that situation. So you would be doing the same thing what we did. You would go through and you would find delta x, like we've been doing, and you would base this on the midpoints instead of left and right. That's what this example is showing. But what would happen on this is if you did the area on all those, you would get positive numbers for all those areas. But when you get into the calculus working the integral out, what we say is if you're below the x-axis, okay, then what happens is this thing we call the net area turns out to be negative. And that's what we're mostly going to talk about, is how that works. This right here, this does not show you the y of that so much, because if you went through and did all of these rectangles and found the areas and you added them up, you would get a positive number, but we define the net area to be negative if it's all below the x-axis. Now once we get into the calculus, that'll begin to make a little bit better sense to you. Okay, the other thing I want to point your attention to in this problem is this. We talked about the sigma notation, and now that's what we're going to kind of be looking at. This thing right here is saying we're summing up rectangles from 1 to 4. That thing right there means there's 4 rectangles, and what we're doing is this right here. This would be, 0.5 would be delta x. And what that is, like we've learned, that's the width of the rectangle. What the function value is going to be the height of the rectangle right there. So you're always going to see this, if you write this in a sigma notation, you're always going to say like k equals 1 to n. N is going to be how many rectangles you have. Then it's always going to be f of x of something. The reason the textbook puts that star there is because that could be different. It could be a midpoint, it could be a left or right endpoint. So that's just sort of a generic notation for it's a function value of whatever we're looking at, midpoint or whatever. And then delta x is the height. So that's kind of important on that. I'm sorry, I said that wrong. Delta x is the width. That's the height like that. Does that make sense, what the notation's saying? That's the number one thing I want you to get out of the sigma stuff, is the notational system that we're going to use for this. Now when we get into calculus, we're just going to change this to this. The sigma is going to become an integral, and we're going to do an integral from 1 to n that's called a definite integral. We haven't done that yet. Then we'll end up having f of x, and instead of delta x, we'll have dx. Okay, that's what's going to happen. And then that's going to allow us to get a precise area. So we're kind of leading up to that idea, okay? All right, so that's all I want to say on that is since all of those rectangles were below, we use negative values. And what happens on that, the reason for this is when you do these function values, those function values are all negative. That's why we get that then. Okay, does that make sense? Okay, because you're doing f of x times delta x. Delta x is always positive. It always is. But sometimes the function's negative. So that's negative. That area is represented by a negative number. Okay, does that make sense? Okay. All right. So let's do the next page is just kind of another example. I'm not going to talk much about this other than the notation. So in this one, key thing is I want you to understand the notation on this. So what happens on this one is you're doing, this one's left Reimann sums. So you got left endpoints on those rectangles like that. Now what's going to happen on this is essentially this. These are above the x-axis. So when you do those areas of those rectangles, they're going to be positive, right? Because you're going to have positive function values. There's a rectangle there. What's the area of that rectangle? It's 0. Okay, that happens sometimes. And all these things here, since the function values are negative, you're going to get negative values for the area. Okay, that's how that works out when you do those Reimann sums. So what's happening on this is when you look at this notation, we're going k equals 1 to 6. The 6 means there's 6 rectangles is what we have. And then if you go through and calculate this out, delta x would end up being 0.5. That 0.5 is the width. And then what you would have on this, if you worked out the details, what I'm trying to show you without going through this too much, is when you did this right here, those would be positive numbers. That would be above the curve. When you do this little piece right there, you get 0 area. That's that part that's just a line, right? Then if you look at this, those are going to be the negatives like that. So you would end up with a negative answer for this problem. And the reason is this. Which part do we have more area on? Above the x-axis or below the x-axis? Below. So we have a net area that's negative. Does that make sense? Okay, so a lot of times if you're doing an area under a curve, because you're always looking at the x-axis and the curve, you can end up with negative answers. Okay, that's what we're kind of focusing on this section, basically. Okay, so to begin with then, this next one, again, the only thing I want you to just kind of pay attention on this is that's where you're going to get positive answers, and that's where you're going to get negative answers. And then the net area on this, you would just have a positive plus a negative, and then plus a positive. Okay, that one right there, sometimes they can balance out perfectly and you get a net area of 0. That can happen also. Okay? All right, does that make sense what I'm saying then? Okay, the negative comes from a negative function value. That's how we get that. Okay, now here's what net area is, and I'm going to kind of, we'll start getting into some examples here. Okay, so what this is saying is the net area just says this. This is the key thing here. It's the part that lies above the x-axis minus the areas that are below the x-axis. Okay, so it's always like that. So that's net area. Area is not negative. Okay, but when you do net area, it can be negative. If we're doing individual areas, or if we're doing like a sum of all the absolute values of the area, then we could get a positive value. Okay, so that's the idea. Okay, so let's see. That's mostly what I want to show you on that, and these are just sort of some ideas of showing you how the rectangles work, like with 6 subintervals versus 40 subintervals and so forth. So the idea is this one is more accurate than that one, correct? Everybody understand that? Okay, we've already talked about that, okay? All right, and then in calculus, the idea is going to be is we want to go like this. We want to go k equals 1 to infinity. We want an infinite number of rectangles, and when we have that, then it'll be perfect. Okay, it's pretty bizarre, but that's the way it works out. Okay, we can sum up an infinite number of numbers and get a finite answer. Pretty wild, isn't it? Okay, that's what we talk about in Calc 2 all the time. We have these series, and we talk about whether they converge to an answer or they don't converge to an answer. Okay, so what I'm going to introduce you to then on the next page is the definite integral. And kind of look at this. We haven't seen this yet, but basically you'll have these two numbers here like a to b. And that would be the region you're interested in that area on. So what this is, and what you want to do is you want to kind of make a basic connection on this. So this is more what you guys are doing. You're doing a finite number of rectangles. Okay, that's just, you're going from one to however many rectangles. So that's finite. So that gives an estimation. Okay, when we do an integral, we do this. Okay, the f of x is still there, and like I said a few minutes ago, the delta x becomes dx, and basically what happens on dx is it just goes to 0. The width never hits 0, but it can get as close to 0 as we want it to be. Okay, so it's still the same thing. That mysterious dx, and I basically have told you so far to just think of that as notation. It's not really notation. What it's representing, again, is the width of the rectangle, but it's tiny. Goes to 0. And then that right there, f of x, again, is the height. And then what you're doing here is this is the interval that you're interested in from a to b, whatever, okay? And these are just some terminology. We call these the limits of integration, okay, is what that is. All right, so let's see. We're going to look a little bit down here. I want to look a little bit at some more specific things. And so if you had something kind of like this, okay, you could end up having a function, and that function could be broken up into pieces. Like, for instance, this function right here is discontinuous at 2 places. There's 2 places where there's a break in a graph. So you can still integrate it, okay? And the idea with that would be is you could just break it up into subregions. So you could do that integral right there. You could do this integral here, and then this one here. And what you would really be doing when you get this net area on this, it would go like this. You would say positive 1, because that's above the x-axis. That would be minus 2, because it's below. This is probably not drawn to scale. And then it would be plus 3, like that. So that net area would be, what is that, 2. That's how that goes. All right. Now, that's not the total area. The total area, that's kind of a difference between net and total. Total area would just be 1 plus absolute value of negative 2 plus 3. So that would be 6, like that. See, there's a difference. Mostly what we're dealing with integrals is net area. Okay? And that's because the areas below the x-axis are negative numbers. Okay, does that make sense?
Say that one more time.
Okay, net area goes like this. Okay, anything that's above the x-axis, you're going to use a positive value for the area. Anything below, you're going to use a negative. That's why I put a negative 2 there. Okay.
So net area is everything above the x-axis?
If it's under the x-axis, you're going to use a negative for that area. And the reason is because when you do f of x times dx, f of x is negative. See, all these function values down here are negative, aren't they?
Right. Yeah.
That's why. All these function values here are positive. So what you're always doing on a rectangle is you're doing base times height. Well, the height is positive here because the function value is positive. But if you look down here, it's still base times height. Now the height has a negative number because it's a function value.
Right.
So that's why we do that. So net area, we go ahead and use the negative there. If I just say total area, then we're going to go ahead and just use all positive numbers. Mostly what we're dealing with is net area.
So net area is everything below the x-axis? Is that what is the
Net area is just the total of all that, but you use a positive in that case. You use a negative there, and you use a positive there. So what I'm doing is positive 1, because that's above the curve, plus a negative 2, because that's below the curve. Then I use plus whatever that was, 3, for that reason. Okay, that's what it is. Okay, all right. Now we're going to do a bunch of this here in a minute to kind of get everybody this idea established. Okay, now what I'm going to do here on this next page is kind of get the idea of how you could do this area. We're not quite ready to do the integral yet. It takes us a while to lead up to actually what the integral is doing. So this one right here, the first thing I want you to do is start by just graphing this function. So the function is y equals 2x plus 3. Now you don't need a graphing calculator on that because it's a line, right? It has a y-intercept of 3 and it has a slope of 2. Okay, so we're just going to go ahead and graph that, starting with 3. Okay, like that, just put a dot there. Okay, then go up 2 and over 1. Go ahead and just do this accurately because we need to. So up 2 over 1, up 2 over 1, and until we run out of room. Now, I think we're supposed to go all the way from 2 to 4. So I'm going to take that up one more notch and kind of go like that. All right. So what we want to do with that then is we want to go ahead and just sketch that line out. So I'm going to go ahead and just put my line there like that. And what we're doing on this, partially what you're learning here is what does this mean? This means the area under the curve from 2 to 4. So what we're going to do is I want you to go to 2, go up there and kind of go there, kind of highlight that dot, and then go straight down like that. All right, that'll be where the 2 is. That's the lower limit of integration. Then go out to the 4. So go way up there to that point right there and go straight down like that, and then draw like a width right there, and then you can shade this in. This is the area that we're trying to find. And we're not ready to do use the integral to do that. We're just going to use basic formulas. So the area under this curve is going to be represented by A. Okay? What kind of shape is that? It's what? I always ask because a lot of times students don't know. It's a trapezoid, okay? It's a trapezoid. A trapezoid's a four-sided figure where one set is parallel, the other set are not parallel. That's the idea. Okay, so this is a trapezoid. So actually what we're going to do is we're just going to use the formula for the area of a trapezoid. Okay, and the formula for that, if you don't know that, is 1/2 the height times the sum of the bases. Okay, so that right there, if you don't know that, that's the height. And then these two things right here are the bases. You have two bases on a there we go, bases, okay? All right, so what we're going to do is just apply that formula. So what we're really doing in this is the height on this, and you just do this by looking at that, the height is equal to 2. And what a height is, don't think of a height as straight up and down. That's kind of a narrow approach to that. What it is that's how far apart are the bases. And the bases are these things. So this thing right here, we could call that base 1 or base 2. It doesn't matter. And then this thing right here, we could call that base 2. Okay, so we just basically are going to crunch this out and find that area. All right. Well, if you did the function values on this, like this point right here, if you did that function value, we would end up with f of 2 is going to be equal to 7. You can tell on your graph that that y value is 7. This point right here is f of 4, okay, because remember, we're going from 2 to 4. That's why I'm going to 4. And if you plugged in a 4 here, you'd have 2 times 4 plus 3, which would be 12 plus 3, 8 plus 3, or 11. So that would be 11 right there. Okay? You guys see what I'm doing? Okay? All right, so now we just crunch it out. Okay, so what we'd have is the area of the trapezoid would be 1/2 the height. What was the height? 2. Okay, that's the distance between the parallel bases. And then what are the bases? How tall is this one right here?
7.
That one, this one?
Oh,
11. How tall is the other one?
7.
Doesn't matter which is which though, okay? So we can just say that one is 11, that one's 7, or backwards. See, that's what the function value is doing, is it's giving you the height. That's what I'm trying to show you partially on this. That would cancel out, so that gives the area of the trapezoid would be 18. So we say the net area is 18. And it's all positive because it's all above the x-axis. And it came from the fact that that's positive, and that's positive. Okay, that's why we have that situation. If the function values are positive, then you're going to get a positive number for the area. That's the idea. Okay, everybody understand that okay? All right, that's not too bad. Let's do this next one here. So this one I'm going to try to, what I'm doing is I'm making these functions represent areas that are basic geometric formulas you know from your background. So with this one, go ahead and plot the line. You don't need your graphing calculator, just plot it. So this has got a y-intercept of -6, it looks like. Then the slope's 2, or 2 over 1, so you can just kind of carefully count up 2 over 1. And do that kind of carefully so we can get a real good representation of this. Okay, and kind of until you run out of room, and then you can go ahead and, if you want to, go ahead and connect that line. Okay, kind of like that. Okay, now what we're going to do is partially what we're doing in this problem is we're trying to understand the notation of that integral. So we're finding the area from where to where? 1 to 6, good. Okay, so 1 to 6, those are the limits of the integration. They're going to tell you that, okay? So here's what you want to do with this. We want to start with 1, and then you want to figure out your area. This time, are you going to have area below the x-axis? Yeah, absolutely. So if you go to 1 to 3, so if you just kind of go straight down like that, you're going to have a triangle. So I'm going to highlight that in yellow. That's going to be like your first region. So I'll just call that like region 1, R1 for region 1. Okay, so that's going to be the first. Okay, and then we're going to go all the way from 4 to 6 now. So now we go, or I'm sorry, 3 to 6. So now we need to go from 3 to 6. Once you get to 6, just go straight up to the function. And then I'm going to shade that in, and then that's going to be the second region, kind of like that. Okay, so I'll call that R2 for region 2. Okay, like that. Okay, now, what we have is we have triangles, right? You have two triangles, and you have to know that formula. So what's the formula for an area of a triangle? 1/2 base times height, okay? Or if you want to, a lot of times I just say base times height over 2. It's the same thing, okay? So what we need to do is we need to find the area of region 1, okay, and do that. Now, if we do that, that's 1/2 base times height. So if you look at this, that's the yellow right here. Well, okay, the base and height are interchangeable. These are right triangles. So you could call this the base if you want to. And that base right there looks like 2, right? Okay. The height would be like the function value. And this is where you get the negative here. So it looks to me like that function value is down what? 1, 2, 3, is that 4? Okay, but we'd use -4 because see what that is that's f of 1. Okay, so you're going to get a negative value. All right, so when we do that, the 2's are going to cross out, so you're going to get -4. So what you're going to get is region 1, the area of region 1 is going to be represented by -4. And you already knew that, right? How come? It's below the x-axis. Okay, if that region's below the x-axis, you're going to get a negative value for that area. Okay, because that height is represented by a negative value. Okay, that's the key. Okay, now let's go to the area of region 2. Okay, again, that's 1/2 base times height. Okay, so let's see. On this one, the base, what does that look like to you? That looks like 3. The distance from 3 to 6 is 3. Okay, we got that. Now the height is the function value. So if we do that function value, that looks like, is that 6? Okay, so we got that. Okay, so that's just really half of 18. So that's 9. Okay, so that's what we would get there then. Okay, all right. Does that look okay? Yeah, that should be okay. All right, so what we have then is this. We have the area of region 2 is equal to +9. And that's a positive. Why is it positive? Because it's above the x-axis. Okay, so the net area, just add them together. -4 plus 9, that's going to give you a net area of 5. Okay, and if you look at the diagram, we had more area above the x-axis, correct? That's why we ended up with a positive answer. Okay, does that make sense to everybody now? Okay, so that's the idea. Okay, let's see where we're at here. Let's do a couple of other things here, then we'll take a break. I think I want to just finish up this page, then we'll just talk about this, and we'll take a break because I want to get through this example here. Okay, okay, just to kind of wrap this up. Okay, so here's what you're trying to do. The purpose of this exercise is to help you understand how area works and how the integral works. So this integral, you're going from A to B. Okay, and they're telling you that the area of that region's 12. So would the answer be 12 or -12?
12.
It'd be 12. Okay, it's above the x-axis, that's why it's positive. Okay, the next problem, you're going from B to C. Okay, so what are you going to get there? -10, right? Okay, -10. That's basically what you're trying to get accomplished in your head now. Okay, now the next one, what we're doing is we're doing A to C. So what you have is you have 2 regions. On this you have 12. What are you going to use there? -12. So what you got to do is you got to break it up. See, what you're really doing is you're doing this. I do want you to write this down like this. You're going to go from A to B of f of x dx, then you're going to go from B to C of f of x dx. That's what you're really doing on that, is you're looking at two regions. The first one is 12, the second one is -10, so that net area would be +2. You have a little bit more area on above the x-axis than you do the bottom. Okay, so that's the idea. All right, next one, B to D. Okay, so again, on this one, B to D, you can do this in your head. Can you tell me what the net area would be from B to D? Be -2, wouldn't it? Okay, so the idea is what you're doing with this, and you can write the integral down as you're going B to C of f of x dx. Then you're adding on the integral from c to d, f of x dx. Okay, so f of x is going to be, the first one is going to be negative 10. The second one's going to be 8, so that's going to be negative 2. So you know that you have more area under the curve, under the x-axis than you do above, so that's why you get a negative net area. Okay, does that make sense to everybody?
Yep.
Okay, now see that negative comes from negative function values. That's the idea. Okay, here. So I'm going to talk about what these two things are, these two integral rules here. And kind of look at this. Okay, so what this first rule is saying is, like, if you had something like, just write down an example like this. Just say that you had the integral from 1 to 2 of f of x dx, and let's just say the answer turned out to be 5, okay? Well, if you change the limits of integration backwards, like that, you just get the opposite answer, okay? That's actually easier to explain once you learn how to work out a definite integral. But basically what's happening is if you change the direction on that, then you're going to end up having an opposite value. This one right here is very easy to explain. So if you had an integral from, say, 2 to 2 of f of x dx, that's equal to 0. Does that make sense why that would be? You know, if you did an area under a curve, okay, like this. So if you did an area under a curve, say you had some curve like this, f of x. And you have, like, that's x and that's your y-axis. And let's say that you were integrating from 2 to 2. What would you have? You'd have kind of like a little strip there, okay? In fact, the width would be 0. So you would actually, if you had base times height, you would end up having 0 times whatever the height is, so it'd be 0. Okay, does that make sense? It's got to be, okay? There's not even a rectangle there. There's just a line, and a line doesn't have any width to it, okay? So that's the idea. We've talked about this a little bit, so what this is showing is if you're doing an integral from a to b, sometimes it's necessary to break it up into two integrals. So you could go a to p and then p to b. So you basically got this big region here, and then you could have these little subregions like A1 and A2. So basically that area there would be the area of the 1 plus the area of 2, like that. So that's what that's saying. Okay, does that make sense? Does that seem logical? Okay, all right, okay. All right, let's see. So these are kind of the basic integral rules. We've already really talked about all those. That's the one that I just talked about. Integrate from a to a, you get 0. Integrate from a to b, change those things backwards. B to a to b, you get an opposite answer. Okay, you'll see that. You can break an integral of a sum into the sum of the integrals. We talked about that. And then this kind of works like a limit or like a derivative. If you have a constant multiplied by your function, then you can bring that out of the integral. That works the same way like on a summation also. And then this one is just saying the diagram that I did on the previous page. It's just saying you can break an integral up into two pieces where that p would represent some number in the middle. Okay? So to get us comfortable with these properties, this next exercise right here, that's the purpose of it, is to give you practice in understanding the properties. And what I'm doing on this one, see, I still haven't even shown you how to do an integral yet, but we'll get into that next week, is I'm giving you this piece of information. I'm giving you that the integral of 3x 4 minus x is 32, okay? Now notice down here I'm giving you things very similar. Here I've got the same thing, 3x 4 minus x. Here I've got just x 4 minus x and so forth. So they're very similar. So from this and from the rules, we should be able to figure this out okay. All right? So here's what we have here. What is the only difference between that integral and the one I gave you?
0.4.
I changed the things, okay? I changed the limit. So what's the answer? It's not 32. What is it? It's negative 32. Okay? That's that first property right there. That's property 1. So I'm going to also have you say by property 1, because that's what we're trying to do, is get comfortable with these properties of integrals. Okay? All right, the next one, okay? Well, what's the difference between this integral and the one I gave you? You got a 3 there, okay? So here's the way you could handle this. Okay, so one thing you could do, this is the way I'm going to choose to do this, just go ahead and write down the integral I gave you. And don't be lazy about that dx. That dx has to be there. Students a lot of times just kind of get lazy and quit putting it there. You need to have that there. Okay, what I want is I want a 3. So what I'm going to do is I'm going to put a 3 in there. But I've changed the problem. So what I can do to keep from changing the problem is I could put a 1/3 there, right? Because, see, you can bring this outside. You can bring that 3 outside, and if you brought that 3 outside, it would cancel with the 1/3, and you would have the same integral, right? So I haven't changed anything. Okay, so how would you get the final answer then?
32 divided by 2?
Absolutely. You would do 1/3 of 32. Okay, because we already know that the answer to this integral is 32 because I gave it to you.
But it's x minus 4 instead of 4 minus x.
Oh, I didn't see that, so the teacher wasn't paying attention. Okay. So let's pay attention to that, okay? Let me show you how you'd have to handle that now. Okay? Thank you. All right, so let's try that again, okay? All right, so here's what I'm going to do. All right, when you've learned how to do this like in algebra, if you turn something around, like if you change this around to x minus 4, what do you got to do to keep from changing the problem? You have to have a negative in front, right? Does that make sense? You have a negative x plus 4, same thing. So what I'm going to do is I'm going to change this. Since this is an x minus 4, you can do it one of 2 ways. If you want to just change this, I'm going to actually change this one around here like this so that that now says 4 minus x. So it matches that, right? Now what that's going to cause us to do is put a negative there. Now I haven't changed the problem. See what you want to do on this. If you don't understand what I'm doing, just double check this, okay? It's just, if you multiply it out, it's going to be the same thing, okay? Now what I can do is, that's really a constant. You can bring a negative out of an integral. So you could write this now as negative the integral from 0 to 4 of 3x times 4 minus x dx. So see what we're trying to do is we're just trying to match this integral with this integral. Now we did it. So what's the answer to this problem? No, there was already a 3 there, right?
Well, it's not a 3rd in your B.
Oh, yeah. Now, what am I doing? I just added a 3 in there, so I got the 3rd. You're right. Okay, so I need to do this. Okay, I got so excited about changing that backwards, then I forgot about that. So, yeah, we go 3, then you have to have a negative, then a 1/3 like that. Okay, like that. All right, it's the same. All right, that's a little tricky. But be sure that when you turn the order you subtract something around that you put a negative in front of it. Okay, does it look good now? I think it's exactly the same integral now. Okay, so what the answer would be negative 1/3 times 32. So that's going to be negative 32 over 3. Okay, that's how that would go. Okay, that would be the idea. Okay, I'm going to be a little bit more careful this time and make sure I identify all the differences. Okay, so what do you see that's different about this integral? Let's see, the limits are backwards, number 1. That's the first thing I see that it's different. So those are backwards. What else? Yeah, the 6 is kind of doubled that, right? Okay, so what I try to do when I do these problems is try to change this so that it's like this. So I'm going to do a couple of things. First thing I'm going to do is if I change the limits of integration, if I just deal with that first of all, I would have 0 to 4, but that would be a negative. Anytime you change the limits of integration, then you do that. So that's step 1. I'm just going to do this in 2 steps. Okay, so you have that, right? Okay, now the next thing I can do on this is you could break that up into 2 times 3, right? And if you did that, the 2 is a constant, so it could come out in front. So what you would have is negative 2 times the integral from 0 to 4, and now that would just be a 3x. Now I think everything matches perfectly, right? Okay, so that's what I'm trying to do is make this thing match that thing. Okay, so now what would you do to get the answer? Yeah, negative 2 times 32. Okay, like that. All right, and then that would be what? Negative 96. Okay, no, negative 64. Okay, like that. All right, we good? Okay.
So when we changed the limits, the 0 and the 4, you just make it a negative?
Right. Yeah, that's property 1. So if you look at the properties we're learning, that's what I did when I or property 2, is I switched the order the limits were in. Okay, then I can take a constant out. So I really used property 2 and property 4 on that problem. Okay. Okay, let's see the next one now. Now with this next one, I think I left something off of this thing because it's going from 0 to 8. So really what you could do on this now is you could first of all do this like this. You could say, okay, we can do the integral from 0 to 4 of 3x times 4 minus x dx. So you can do that. And then you would have a second integral here, which would end up going from 4 to 8 of 3x times 4 minus x dx like that. So you can do that. Okay, you can break that 0, 8 up into 0 to 4 and then 4 to 8. Okay, but you know this, right? I gave that to you. That integral right there is 32. So you would end up having 32 for that integral. But then this thing right here, there's not really enough information in there to go through and figure this integral out, because that area, see, this is a parabola. That's some sort of a quadratic. So its area is not necessarily going to be the same thing as 32. It could possibly be, depending on the symmetry. So I'm going to show you something on a graphing calculator with this one. But right now, as of now, that's basically all I can conclude. Okay, now I'm going to do this one on the graphing calculator. Because you're probably going to have a symmetry on this, and you probably understand this best this way. So if I just do 3x and then times 4 minus x, like this, and if I graph that, now I'm going to graph it from 0 to 8. Okay, you might already know this. You could kind of figure out what's happening at 4 on this thing. There's something special that's happening on 4. So I'm going to go 0 to 8 by a scale of 1. And then from there, I think I'll just go like something like 0 to, let me just look at the table of values real quick on this. Let's see what we got. So let's see, we have some negative numbers in there too. So let's go like this. For the y's, let's go like negative 100. To 100. I think I was looking at that table. Okay, I'm going to try to do it like this. You don't have to do this. I just want to see if this thing has a certain symmetry to it. And it doesn't look like it does. I thought it might. So see, this part right here is the 32. All right. So what I'm going to do real quick is I'm going to show you this, because I've already taught you I'll do this on the calculator. So if you did this option 7 and you went 0 to 4, okay, well then what you would end up having, that should be the 32, assuming I put that in there correctly. So that's what that is. That's what you were given. But how about this area from 4 to 8? Is it the same, or is it like totally different?
Totally different.
It's totally different. So at this stage, there really wouldn't be anything you could do there, okay, because you don't really know how to do a definite integral yet. So you just stop there. That's all you could do. Okay, that's it.
Can you do trig functions with these?
Oh, yeah. Yeah, you can do any function that you've ever learned about, okay, and more, okay? All right, so let's do this next thing here, and then we'll try to get this thing wrapped up here, okay? Okay, so with this one, okay, what I've done here is I've given you 2 integrals now. So I want to look at these 2 things right here and finish this up. So we're going to use just basic properties. On this, you can bring the 3 out. That's a constant. So you want to write that as negative 3 times the integral 1 to 4 of f of x dx, f of x dx like that. Okay? Now notice I gave you this integral right here. That integral from 1 to 4 of f of x dx is 8. So that would be negative 3 times 8. So that's going to be negative 24 is what you should get there then. Okay? So that would be the answer on that one. Okay? And then for 40, the next one, same idea. Okay, you just bring that out. That would be 3 times the integral from 1 to 4 f of x dx. Okay, we already know what the integral from 1 to 4 is. That's 8. So that's 3 times 8. So that's 24. Okay, all right. Now the next one right here, I think I gave you, this is 12 times that. So there's a couple of things going on in this problem that you have to pay attention to. Number one, you could take that 12 out. And then also the limits are different. You have the limits from 6 to 4, but you have two integrals. You have an integral from 1 to 4 and 1 to 6. So you have to kind of set up some sort of an equation when you do this then, okay? So one thing that you could do on this is, first of all, you could change this. And I'm going to go ahead and do this like this. I'm going to go ahead and change these limits from 4 to 6. If I do that, what changes? It becomes negative. Okay, and you can go ahead and take that 12 out too while you're doing that. I'm just going to start it this way then. So I have negative 12, change the limits backwards, then I have f of x dx like that. Okay, now what I got to do is from these two integrals, I should be able to figure out what this area is. Because if you look at this, and I'm just going to write this kind of at the side, if you have the integral from 1 to 6, f of x dx, okay, you could break it up this way. You could break it up into the integral from 1 to 4 of f of x dx plus the integral from 4 to 6 f of x dx, okay? This is kind of what the reason I'm doing this is so I can come up with a simple equation. So that integral right there is 1 to 6. This thing was given as 5, right? Okay, this integral from 1 to 4 was given as 8. This is the integral we're trying to find anyway, right? Okay, so that's what we're trying to do. Okay, does that make sense what I'm doing? Okay, well, all you do is just subtract 8 from both sides, so you would have 5 minus 8 is negative 3. So that's what that integral is then. So the integral from 6 to 4, f of dx, is negative 3. So that's negative 12 times negative 3. So that's going to be 36. Okay, like that. Is that logical? Okay, I'm setting up equations. I've given you enough information to figure out. If I gave you 1 to 4 and 1 to 6, then you can find that piece. Okay, that's the idea. Okay? All right, now that we have that, so we did, this one's real easy to do now. This one you just bring out the 3, and then you would have the integral 4 to 6, f of x dx, so that's going to be 3 times, and let's see, that integral from 4 to 6 was negative 3 now, so that'll give a negative 9. Okay? So those are kind of good little exercises that make you think through the properties fairly well. Now I've done probably enough of this that we can go ahead and start our review. So I'm going to go ahead and just close that off.